Okay.
Thank you, Raj.
Right. Well, thanks for the introduction. I think you pretty much said everything I need to say in my introduction. So the only other background information is this slide deck presentation was originally put together for my early stage assessment at Imperial College, which is roughly analogous to the, I believe it's called the transfer viva at UCL. So we're going to do quite a lot of background before we get into the meat of things, but it'll help set the scene for why I'm working on this project. So some background to actually who funds this, which is kind of one of the most important things. My work is funded by the Dementia Research Institute, the DRI, specifically the Care Research and Technology Center, which is most of the DRI is focused on biomedical applications like heavy drug development and neurochemical processes. The CRT branch is actually looking more into care technologies. So the overall aim of the DRI is put out there is to accelerate, innovate, deepen, and broaden discovery science in dementia with the goal of filling the huge knowledge gap in this field. And part of this is, part of the CRT focus is on creating safe and secure systems to move the point of care into the home. It's one of the big pushes is to really shape this dynamic of dementia from something that is cared for to something that can be cared for in the home. So some more motivation. You're probably already familiar with this because it's a quite well understood topic, but briefly to cover it, dementia is a very big problem. It's a very debilitating condition that affects people's ability to live at home independently. It is growing and increasing, so the incidence of dementia is, with the aging population, expanding, and care budgets and care resources are not expanding as the population grows. And key to studying care is reliable long-term non-invasive data, generating that data to both inform care and research into new strategies of care or treatments. So to fill this need, currently there are a bunch of sensing methods used both commercially and in research to create long-term monitoring data on these individuals. Most prominently, of course, and there's been the longest history, is in-person care, which is expensive and also fundamentally intrusive. You're having someone else coming into your house. And as far as data generation goes, it's not very reliable to have an individual necessarily reporting this kind of data. Next, you have cameras, which are very invasive and also require a lot of image processing to get any useful data out of them. They're less of a passive data gathering and more, you're probably going to need at some point a human in the loop to verify the data that you're getting. Next, we have very sparse sensing like door sensors and plug sensors that can sense when an appliance is being used. These generate quite low quality data. It's sparse, you only get point events, and there's only so much it can really tell you. And then finally, we have wearables, things like smartwatches, which do produce very high quality data. You can get good movement data, good heart rate data, all sorts of things, but they put a high burden on the patient, and it's quite difficult to get long-term compliance with these things, especially in a population with a mental condition where you're getting lower compliance, and basically you end up with patchy data or no data when it's not used. So the opportunity, biomedical radar. I'm a bit preaching to the choir here, so I'll skip a bit lightly over this. But there has been an increasing interest in biomedical radar. There are even some commercial products out there already that are in this field. I've highlighted two here. We've got Cicadia bedside monitor and the Somnify bedside monitor. Something all the current systems that are at least commercially available have in common is they are one sensor in one place, kind of sensing a thing. Both these two are focused on sleep sensing. So while they may do respiration and heart rate as well, their fundamental purpose is to improve sleep quality or monitor sleep quality. And you may find various other sensors. There are fall detection systems which just do fall detection. But fundamentally, they're quite a limited range of features and quite a limited range of coverage, as it is a single sensor in a place. So this brings us to the opportunity that I'm hoping to address through some of my work, which is these very low-cost SoC radar sensors and very low-cost SoC Wi-Fi systems. So two quick examples of these radars would be the Novelda X4 and the Aconir XM132. 132. These exist either in the ultra-wide bands or the ISM bands, ultra-wide band, they're ultra-wide radars, or they sit in the ISM band, which essentially makes them license-free in terms of practicality, which means we don't have to license the use of these. We can just buy them off the shelf, put them in our application, and carry on. And of course, the Wi-Fi SoCs are, with the ESP32 especially, is becoming almost ubiquitous. It's hard now to buy some devices without Wi-Fi connectivity, and it really has not been explored in connection with some of these cheap radars. As far as I can find, I haven't found examples in the literature of networked systems. So the opportunity is taking these two cheap technologies and putting them together and looking at, can we improve the data from these cheap radar sensors by using more of them and by putting them in more places? So could we put one in each room of a house? Can we put multiple in each rooms, and see what kind of improvement that can give us? So continuing with a very structured approach, here is our research objectives, defending my intentions for my PhD. But the first research objective is to develop this networked SoC radar system and generate some data. Because right now, as far as I can find, there has not been a networked SoC radar system of this type, networked with Wi-Fi, that's kind of like each individual sensor acting on its own. Next, you need to validate that with some basic signal processing to analyze the data to show that it's actually useful. And it's kind of tied into 3 to show some basic clinically relevant measures. So that's things like heart rate, rest rate, fall detection. Then there comes the actually exciting research stuff, I think, with fusing data from multiple sensors into a single representation. So there's multiple different approaches you can take there. But again, this is a system where it's not been done before. So this starts to get exciting. And then 5 and 6 are a bit more back to the utility of the system. We need to be sure we can locate and track individuals throughout multiple environments and recognize who they are, because often you'll have a person with dementia living with their partner, with a carer. And if you can't tell who's generating the data, it's a bit useless. Right, some challenges. So these are all fairly radar agnostic challenges, but we are sensing indoors. There is a lot of clutter. There are chairs, there are things that move around, there are cats. So when you get a range profile, as I have up here, this is from the X4, you can't see a human in there. They're somewhere in that clutter. And separating out what are actual reflections from a human and what are reflections from a chair is kind of the first step. Next, of course, going straight into that, we have multipath, massive multipath, because you're observing a human in a box. And there are reflections of everything. This thing on the right I have is actually a recording from me walking around a completely empty room, and you can still see very strong multipath returns off just the floor and walls. Those are kind of the initial signal processing challenges, and then we have the more advanced challenges of locating and tracking, which kind of assumes we've solved these 2 problems already. And then recognizing and differentiating different people, which becomes kind of a stats machine learning problem. And I'm going to talk a bit less about those. I apologize for this slide. This is me needing to have a slide to talk about all these things in case my examiner's really questioned about it. So I will skip a little lightly over this, but these are some of the fundamental questions and solutions I propose to some of these problems. Fundamentally, when it comes to clutter suppression, you've got 2 options. You can kind of just go for moving targets. So you've got MTI, other filters like that. And then you've got we're actually going to take the static background that we assume is static and remove it from the signal and try and look at the delta between the static background and the dynamic signals. And there's different ways of doing this. Some approaches use wavelets, some have adaptive processes that are, some of which are used on image processing as well. There's a lot of stuff used on green screens and not green screens to remove static backgrounds, but there are different approaches there to use. Mitigating multipath. There are many established techniques for this, some of which I'm still evaluating, but we also have a big advantage of spatial diversity. We can have a sensor on one wall, a sensor on another wall, and they can have different multipath characteristics. So by comparing these, we can hope to reduce that, or just using these in, say, a back projection reduces multipath significantly. The multiple detection types kind of feeds into the challenge of clutter. If you're never really going to have just a nice track or a nice detection on a human, so you're going to have a problem of when the human stops moving. Keeping that track active is probably going to involve fusing active human movements with vital sign recognition. So when someone's static, you can still detect their heartbeat, you can still detect their respiration, and that will be fed into a single tracker probably from these two different sorts of detections, which will need to be weighted. Could be a Kalman filter. In my experimentations, they've not worked great. So maybe an extended Kalman filter or onto a proper full Bayesian tracker. And then finally, we have this identifiability problem, because the whole point of the system is to be cheap and lightweight and reliable. So my aim is to avoid deep neural networks or CNNs, and to keep everything in a purely stats-based process, deterministic process, using SVMs, KNNs to make these distinguishments between different people. That is something I don't yet have a lot of data on. One of my colleagues has done some work on gate analysis using these radars that work very well with just SVMs and KNNs, but that's a couple of years in the future at this point. So finally, some exciting stuff. This is what I've built. This is the network system. I called it Tiresias because I like Greek mythology. Tiresias was a blind prophet. He couldn't see, but he could tell the future. So the system is based around the Novelda X4 because they are the sensors that we had. My lab has an agreement with Novelda already to get these sensors for cheap, so these are what I was working with. It's the actual hardware is quite simple. It's a Raspberry Pi, Pi Zero, so it has all the Wi-Fi network, or it has all the clocks built into it that I need. And the whole system is basically, it's not quite edge computing. Each sensor basically is capturing data, timestamping it, and sending it over the network to the supervisor. This is an old picture. This is when I was still making my own network layer. Don't ever do that. I wrote this whole protocol using UDP sockets and TCP sockets to transfer data around. It was a complete nightmare. It never worked properly. The data transfer rate was great, but it was unreliable. I eventually scrapped the whole thing, and now the whole system uses HTTP REST to move data around. But the concept is each sensor sits on its own, capturing data, sending it, then there's the supervisor software, which can run on anything, collects all that data, synchronizes it, and starts to do interesting things with it. Processing progress. So I had to talk through this with my examiners. The eagle-eyed among you will spot that this diagram is actually wrong. Hilbert transform and the absolute are the wrong way around, but none of my examiners spotted that. This is a version that's about a year old now that shows how I was taking the raw RF capture from the Novelda radar, doing an energy envelope, MTI, and then either doing fusion with filter back projection or simply doing peak detection with CFAR. This wasn't a great solution. It got some basic results, but there's still a long way to go on actually solving many of the problems that this kind of skirts around. But we did do some quite extensive early testing. So this top right is, I think this was actually end of 2020. It was the very first system I got working in kind of Scrabble to get this working as quickly as I could. This is the system enforcing social distancing at some of our labs. So this is tracking my partner and I. And every time we get a little bit too close, within 2 meters, the system sounds a really annoying alarm. This was kind of a good public engagement way of getting the system out there and showing people that, hey, we can track people in a scene. Other than that, we did some basic relevant measures. So we did location tracking in a room, usually just one individual. Walking speed is quite an interesting measure for clinicians, and that was quite easy to do. Respiration rate was a little more challenging, but the standard techniques did work on this data. And presence detection was a really easy gimme from the first kind of couple of hours of having the system up. That was done. So we qualified the system and got it working. Current deployments and collaborations. So this is was part of a large trial conducted at the University of Surrey. That was in their Surrey Sleep Lab, doing lots of data gathering on sleep participants as part of the larger protocol. So we both got some radar data and some really great gold standard data for ECGs, EMGs. They had a whole suite that we also got to just put radars in, which was really great. It's in our lab at Imperial, so there's one for students to just go in and play with, gather data, do their own work on the recordings. I should talk a little bit about the team here. My work has mostly been focused on getting the system working and showing some basic measures that it can pull out. But I have 2 colleagues, 2 other PhD students that are working on extracting more interesting stuff from the signals. So I've one working on gait analysis. So as well as recognizing people by their gait, can we recognize gait features such as dragging a foot, uneven gait, things like that. My second colleague is working on physiological measures. So we actually in the last couple of weeks proved we can detect sleep apnea with this, which is kind of cool. I've got an MSc student that I'm supervising working on fall detection, improving that for the system. And I have a couple of summer students this year who are going to be coming in to work on other smaller parts of the system as their summer project. So, oh, and finally, it's part of this system is a part of the living lab at the urine CRT hub at White City. So we've actually got the system in quite a few different places already. One last talk about a cool thing before we start wrapping up. One of the things we've been investigating with this system in particular is doing the X4 radar does direct RF sampling. So it sends out a pulse and then tries to directly sample the return. So it doesn't natively produce Doppler data. However, by stacking up a load of frames very quickly and then doing an SDFT in slow time, an analogous measure can be taken. I'm still a bit of a pedant in arguing that this is not technically Doppler because we're not measuring a frequency shift in our return signals, but it does produce spectrums that are almost identical. And that can produce this really nice, this is, I think this is real world data of a walking cycle. Credit to my colleague for this, some really interesting data. This is not yet done on the networking system, but this is kind of cool. So future directions, this is kind of wrapping up, telling you what I've told you. We've got a working networked radar. The development of the signal processing techniques is in progress. We've got a lot of interesting results so far. There's a very long way to go. We've shown some basic clinically relevant measures, and we're working on actually publishing a few papers on that. Next, over the next kind of couple of years comes the really interesting stuff where I've got experimental results, but no real solid stuff. Of the data fusion and then locating, tracking, and recognizing challenges come in. So to wrap up, unobtrusively monitoring people with dementia is a big challenge. It is of significant interest. It's only going to become bigger in the next couple of decades. SoC radar is emerging technology. It's not really been heavily applied to this field yet, and it is really enabling this low-cost access to radar data. Networking that capability is going to make this capability so much more useful, more adaptable, and more powerful. And it's really the direction that we should be going in with this technology. But there are many fundamental research questions yet to be answered and challenges that need to be solved before we can really start getting into the meat and the useful stuff out of this technology. So I think I'll leave it there. Thanks for listening to my spiel on this. I'm happy to take any questions. I have a bunch of backup slides, and if you care, a bunch of references as well.